Hello, good evening, and ulit. Hello, good evening, good morning, and good afternoon sa mga senior high dyan nakikinig sa video na to. Nakikinig at nanonood ng video na to. Okay, so our topic for today is electric flux and Gauss law, part 2 of the continuation of this lesson. Part of the General Physics 2 third quarter for senior high school specialization subject. And of course, ito yung mga objectives. Read na siya, so no need for me to state that again. This is our objective for today. Use Gauss law to infer the electric field due to uniformly distributed charges on long wires, spheres, and large plates. You will understand why these are the three shapes chosen later on. Be still like a mountain and flow like a great river. Lao Tzu. And of course, let's start. Now, this is your equation for electric flux. So, top 1, and the electric field, which is derived from the same equation from top. So, basically, this is the electric field using Gauss law. Now, we start with a long wire, a uniformly charged long wire. And what qualifies uniformly charged long wires? These are conducting wires with current or charged insulator rods. It has to be uniform, of course. So a question is, what is the electric field E from a radius of R, which is the nearest point from a uniformly charged long wire with a charge of Q and a length of L. So, yan ang question. So, we start with the formula, as usual. We start with the Gauss law expression, rearranged in that case, written as the total charges divided by the surface area, in which the point in which you want to measure the electric field is contained. Now, since R, there is a better shape to arrange R is a cylinder rather than a sphere. Kung sphere yan, hindi masasama yung ibang part ng wire. So, it has to be the cylinder. Now, this part of the cylinder is not considered because the electric field coming from that is not perpendicular, so it has to be here. And you come up with the expression of 2 pi RL as the surface area of that cylinder. And it so happened that, if you look at this carefully, you have a ratio of Q over L, which can also be used to be expressed as lambda. And what is that lambda? That is the linear charge density. And of course, the final expression is 2ke lambda over r. Notice the formula is a lot simpler than when using the Coulomb's law equation. So, what is the electric field E from a distance of r of a uniformly charged long wire with a charge of Q and a length of L? So the answer is this. 2k sub E lambda over r with 2k sub E is equal to this expression. You already know the meaning of k sub E if you have arrived to this video. Next, a uniformly charged sphere. A uniformly charged sphere can either be solid or spherical shells, and anyway they are the same because the charges only reside on the surface of the volume, not inside. Okay, so This time, our problem is, what's the electric field E from a distance of r again of a uniformly charged sphere with the radius of q and with the charge q and radius of small letter r. So to solve that, we again use this formula. Okay, the surface area this time of a sphere has to be bigger than the original sphere, at least based on this drawing itself. So notice the surface area of the sphere is still 4 pi r squared, and rearranging that 4 pi e sub o r squared, you come up with exactly the same expression as in Coulomb's law. K sub e q over r squared. So, in general, the expression for the electric field of a uniformly charged sphere is the same as the Coulomb's law with a certain condition. The radius of the sphere, which is the one charge, it has to be less than the r in which you want to find the electric field point. Kasi kung mas maliit ang this one from this one, your answer is just 0 because there's no charge inside. Now this time, we have a uniformly charged plate. A uniformly charged plate usually found in capacitors and is only charged on one side. Okay, so this time, question is, what is the electric field E from a distance of r of a uniformly charged square plate with a charge of q and a length of side L? Okay, so we come up again with the same expression as before. This time, our surface area is just L squared, this one. The side has nothing to do again because parallel ang electric field sa side. It has to be the point at which it is perpendicular. So you have Q over L squared. Now this expression happens to be sigma, which is the same as the area charge density. And notice that the equation has become a lot simpler. And of course, when converted into Coulomb's constant, electrical constant, then we come up with 4 pi k sub e sigma, which notice that medyo slightly longer siya. It's actually simpler kasi multiplication lang. Okay, so we're done with what is the electric field E from distance r of a uniformly charged square plate with a charge q inside L. This is the answer. It's just the area charge density divided by epsilon sub o, or 4 pi k sub o times the charge density. Okay. So we summarize this. It is simpler to use Gauss' law for the solution of electric field of more complicated but symmetric systems. And uniform distribution is a must in this kind of system. So for a charged long wire, which has to be thin and long, we have 2 k sub e lambda over r, with lambda as the linear charge density. For a charged sphere, solid or shell, we have k sub e q over r squared, with the requirement that the radius r, small r, that contains the charge has to be less than the r, which is the point from the center. And of course, for charged plate, the equation is just sigma over epsilon sub o, or 4 pi k sub e times sigma. So notice that the Gauss law has simplified it too much. Okay, for our next video, what we're going to do is we're going to solve some problems concerning all those three shapes. Okay, see you next time. You have that time to subscribe, you hit the notification button, and share this video for others to learn, especially mga senior high students. Okay, this is your Pinoy Physics teacher at your service.